Here's our third example of looking at Newton's first law of motion. And in this case, we have an object right here. Let's say it has mass m, and we have two forces acting on it. F1 pulling in this direction, 45 degrees above the horizontal at 100 newtons, and a second force pulling straight down at 180 newtons. Let's say this is the xy plane, so there's no gravity involved. So I might as well just write that down here. So this is the y plane. This is the x plane. Let's say we're looking top down. This is horizontal. How do we go about doing this? Well, what we need to do here is we need to find out what the net force on the object is first, which means we need to do a vectorial addition, which means that we have to add the x and y components. That means we have to find the x component of F1, and we have to find the y component of F1. So F1 in the y direction and F1 in the x direction. So what are those components equal to? I'm looking for my black pen, which I have in my hand right here. So let's do that. Let's find the x and y components. So F1 in the x direction is equal to F1 times the cosine of 45 degrees. So in this case, it's equal to 100 newtons times the cosine of 45 degrees, which is 0.707, which would be equal to 70.7 newtons. We do the same for the y direction. Of course, at 45 degrees, that's easy. F1y is equal to F1 times the sine of 45 degrees, which is the same as the cosine of 45 degrees, so which is equal to 100 newtons times the sine of 45 degrees, which is 0.707. So this is also 70.7 newtons. So now to find the net force with these two forces, so we have F net in the x direction. Of course, we have to add the x components and the y components together. So F net is equal to, we have F1x plus F2x. And of course, F2 does not have an x component, so we can go ahead and just ignore that. And so simply the x direction, and that would be equal to 70.7 newtons. That is from that component right there. Now adding the y components together, F net in the y direction is equal to F1y plus F2y. Now here we have to be careful. We do have to take into account the direction. F1y is in the positive direction, so that's a positive 70.7 newtons. But F2, the y component, which is the only component F2, is in the negative y direction, so we have to go minus 180 newtons. So this is equal to minus 109.3 newtons. Let's see, if we add 70 to this, we do indeed get 180. So there we go. Those are the x and y components of the resultant, or the net force. So we can now write that F net is equal to 70.7 newtons in the x direction minus 109.3 newtons in the y direction. All right. Now here I violated rules just a little bit because, of course, when we talk about the magnitude of a force, we don't really have a negative quantity, but I just want to write it there to realize that it's pointing in the negative direction. So if I now want to find the magnitude of that force, so we say then the magnitude of F net is equal to the square root of the F net in the x direction squared plus F net in the y direction squared. So that's using Pythagorean theorem to find the magnitude. So it's equal to the square root of the x direction. Let's see, right here that would be 70.7 newtons. We have to square that plus the y direction minus 109.3 newtons squared. Of course, it doesn't matter, that's negative because we're squaring it anyway. So we have 109.3 squared plus 70.7 squared equals, take the square root, and we get 130 newtons, 130 newtons. All right, so now we have the magnitude of the net force, and we also have the direction. Well, not really an angle. If we want to find the direction, notice that if I draw a line like this and draw a line like this, that the net result looks something like this. So this would be F net like this, F net. If I want to know what this angle is, call it phi, I have to use the arctangent, so let's do that. So the angle is equal to the arctangent of the opposite, which would be the F sub y net, F net y, divided by F net x, which is equal to the arctangent of F net y. The magnitude would be 109.3, and that would be 70.7 for the x direction. So let's do that, 109.3 divided by 70.7. Take the arctangent of that. And we get 57.1 degrees. This here would be 57.1 degree. So that's the net force acting on this object, which of course, using Newton's second law, tells us that we would have an acceleration in this direction. So to cancel that out, we have to have an equal and opposite force in the other direction. So if I now have a force, and let's see, I need a different color. Let me use brown. Let's see if this works. There we go. All right, so this is the F needed to cancel out the net force on the object. If I add a third force that is equal in magnitude and opposite direction to this one, then I would have no acceleration. Then Newton's first law says, since there's no net force acting on the object and the object is stationary, it will stay there forever. And so that's the force I would need. So I would need a force of this magnitude pointing in the opposite direction. So if this angle is 57.1 degrees, and I draw the line over here, so this is the alternate angle right there, or the opposite angle right there, so this is 57.1 degree. If it's 57.1 degrees above the negative x-axis with a magnitude of 130 newtons, that force will cancel out this force, and the object would not accelerate. There's another example of how we use the laws of Newton to accomplish that.